students, welcome back to physics online session. So in last class we were discussing on redistribution of the charge. So in case of that redistribution of the charges, if two capacitors are getting connect, means charges will store, means charges will flow from that higher potential to a lower potential. So after that these two capacitors will attain a common potential. So we got that expression for that common potential, as well as we derived that expression for that energy loss in case of capacitors. So in today's class, so let me focus some numericals on common potential, energy loss. So if that n number of identical drops are combined to bigger drops, so already we got that charge on the bigger drop, capacitance of the bigger drop, radius of the bigger drop, and energy of the bigger drop, and energy density, means charge density of the bigger drop. So related to such aspect, so we'll solve certain kind of numericals. Okay, so just we will solve some kind of numericals related to all such formulas. So let me read out the question here. A parallel plate capacitor with air as a dielectric is charged to a potential V using a battery. So without dielectrics or air is act as a dielectrics, its potential value is, so initial potential value is V, V1 V is equal to V here. Removing the battery, the charged capacitor is then connected across a identical uncharged parallel plate capacitor with wax as a dielectric constant K. So in that first situation, V1 is V and C1 is C here, and identical capacitor, and it is uncharged. So uncharged means its potential value is 0. So remember that. So uncharged capacitors means its potential value is 0 here. So charge is 0 means the potential is also 0. Then common potential of both the capacitor is, so dielectric constant K is introduced. So C2 is equal to what? K into C. So common potential C1 V1 plus of C2 V2 divided by C1 plus of C2 here. C1 is C here, V1 is V plus of C2 is K into C, V2 is 0. V2 is 0 means entire term will give 0 here. C1 plus of C2, C plus of K into C, C into V, C I will take it as a common here, 1 plus of K, and common potential is, so V is equal to V. So or you can take this one as a V1, or V1 only you can take that, V1 or V divided by 1 plus of K here. So this is about a common potential. So next one, given a number of capacitors label as C and V here. Okay, number of capacitors are there, its value is, each value is capacitance value is C, each capacitance value is C, and its potential value is V. Find minimum number of capacitors needed to get an arrangement it is equal to C net and V net. So I am having number of capacitors here, so individual value is C here, individual capacitance value is C, and individual potential value is V here. In order to get that net capacitance C net and net potential value as a V net, then how many minimum number of combinations are possible I need to find out. So for that purpose, so first I will consider that, so energy stored here. So for example, so total energy stored, so half of C net here, so net capacitance and net potential V square into net here. So now look at here, so here that in order to get that total energy stored, so number of capacitors are required, so n number of capacitors, so n into C into V square here. So wherever u of t is there, shall I take that half of n into C into V square here? It is equal to half of C net into V square of net. So 1 by 2 term will getting cancelled out. N value I need to find out here. Minimum number they asked that. So what was the question here? Minimum number of capacitors needed to get an arrangement equal to C net and V net. So n is equal to C net divided by C, V square net divided by V here. So minimum number of capacitors required. So n value is C net divided by C and V square net divided by V here. So we'll look at next one. N capacitors of 2 microfarad each. N number of capacitors are there, each value is 2 microfarad here. So each value is 2 microfarad are connected in parallel and potential difference is 200 volt. So all such capacitors are connected in parallel combination. So applying a potential difference of 200 volt to the combination, the total charge on them was 1 coulomb, then N is equal to, so total charge is how much? 1 coulomb here. Then in order to get that these combination, how many number of capacitors are connected, I need to find out here. So look at here. So from the basic definition of capacitance, C is equal to Q by V, or Q is equal to what? C into V. Here N number of capacitors are there. Shall I take that N into C into V here? So I need to find out that N value. Q value is how much? 1 here. N. C value is how much? 2 into 10 to the power of minus 6. So this one is 2 into 10 to the power of 2 here. So N is equal to 1 divided by 2 into 2. 4 into 10 to the power of minus of 4. 1 by 4 means 0.25. 0.25 into, so if it goes to numerator, 10 to the power of 4 here. So 0.25 into 10 to the power of 4. So shall I take that 2 digit and after 2 digit. So 2500 here. So what's that answer here? Number of capacitors are N is equal to what? So N is equal to 2500 here. So we'll look at next one. So hope you are understanding these numericals. So just you list out the formulas. Okay. Okay, we'll look at next one. A condenser of capacity 16 millifarad charged to a potential of 20 volt. So capacitance value is 16 millifarad and it is charged to a potential of 20 volt here. This capacitance is charged by applying a potential of 20 volt connected to a condenser of capacity C charged to a potential of 10 volt as shown in the figure. As shown in the figure, its common potential is 14 volt, then capacitance value is equal to C1 is equal to 16 millifarad, C2 value is C they mention, and V1 value is 20 volt and V2 value is 10 volt here. So the given diagram here, so two capacitors are there, C1 and C2, they are connected in this parallel manner, and in this situation, so it's C1 value they given, V1 value they given, C2 value is equal to C and V2 value they given as a 10 volt. If I connect in this fashion, so it will attain a common potential, its value is 14 volt. Which thing I need to determine here? C2 value I need to determine here. So I am having formula CV is equal to C1 V1 plus of C2 V2 divided by C1 plus of C2, right? So what's that common potential value they mention? 14 here. C1 value is how much? 16 millifarad. 16 into 10 to the power of minus 3 here into V1 is how much? 20 here plus of C2 is C. So this value I need to find out here. So V2 value is how much? Into 10 divided by C1 plus of C2 here. So C1 plus of C2. C1 is 16, C2 is 6 here. 16 plus of C 10 to the power of minus 3 here. Or we can take that. So millifarad as it is only. Capacitance is in millifarad only. No need to take it here. So let me simplify this equation. 14 into 16 plus of 6. It is equal to 16 into 20. 320 here plus of 10C here. Okay, 14 into 16 here, so 14 into 16, so 4, so 224 here. So what's that here? 224 plus of 14C, it is equal to 320 plus of 10C. So I want to find out that C value here. So in order to get that, so look at here. So 14C minus of 10C, it is equal to 320 minus of 224 here. So 14C minus of 10C, so this is 4C here. Okay, so 320 minus of 224, so 4C is equal to 320 minus of 224, 320 minus of 224, so that is 690. So 96 here, C is equal to 96 divided by 4. So C is equal to what? So C is equal to 24 millifarad here. What's that answer here? Capacitance value is 24 millifarad here. So now look at that next one. A 4 microfarad capacitor is charged to a 200 volt battery. So what's the capacitance value here? 4 microfarad capacitor is charged to a potential of 200 volt battery. So V value is how much? So 200 volt battery. It is then disconnected from the supply and it is connected to another uncharged capacitor. So initial one capacitor is there, it is connected to a potential difference of 200 volt and it is disconnected from this supply. They will connect that another uncharged capacitor parallel to that of C1 here. So its value is 2 microfarad here. During this process energy loss is, so they mention that another uncharged capacitor. So uncharged capacitor means its potential value is 0. So which thing they asked determine here? Energy loss here. So what is the connecting formula I am having? 1 by 2 C1 into C2 divided by C1 plus of C2 into V1 minus of V2 of whole square. So fill the value here. C1 is how much? Sorry, C1 is 4 here, C2 is 2 here, microfarad into microfarad, 10 to the power of minus 12, C1 plus of C2 into 10 to the power of minus 6 here, V2 value is 0, V1 square, so 2 into 10 to the power of 2 whole square here, delta of U is equal to half, 8 into 10 to the power of minus 12 into 4 into 10 to the power of 4 divided by 6 into 10 to the power of minus 6 here. So look at here. So delta of U is equal to 8 by 3 into 10 to the power of, so minus 12 plus 6 minus 6 minus 6 plus 4. So that is 10 to the power of minus 2 here. So delta of U is equal to 8 by 3 into 10 to the power of minus 2 here. So 8 by 3, 3 ones are 3 twos are, so 20. So 20 means 3 6 are 18. So that is around about 2.6 into 10 to the power of minus 2 here. So what's that answer here? Delta U is equal to 2.6 into 10 to the power of minus 2 joules here. So this is the energy loss in this situation. So look at here. Initially, so they're having one capacitance. It is connected to a battery of 200 volt and it is disconnected from the battery. And they mention it is connected to another uncharged capacitor, so its V2 value is 0. In this situation, how much energy is lost? I need to find out here. So I got that answer is 2.6 into 10 to the power of minus 2 joules here. Okay, we'll look at next. 3 condensers of capacity 3 millifarad, 6 millifarad and 12 millifarad are connected in series with the battery. So they mention that 3 capacitors are there and these capacitors are connected in a series combination. 3 millifarad, C2 is 6 millifarad, C3 is so 12 millifarad are connected in series with the battery. If charge on 12 millifarad condenser is 24 millicoulomb. So in case of series combination, anyhow charge is remains same here. So Q value is 24 millicoulomb here. Then potential difference across the battery. So V value I need to find out here. First, these capacitors are connected in series combination, means first let me find out that effective capacitance value. So this is the connecting formula. So 1 by C of S is equal to 1 by 3 plus 1 by 6 plus 1 by 12. 1 by C of S is equal to, what's that LCM here? LCM is 12, 4 plus of 2 plus of 1. 7 by 12 here. 1 by C of S is equal to 7 by 12. So look at here. 1 by C of S is equal to 7 by 12. C of S is equal to what? So that is 12 by 7 millifarad. Okay. In case of series combination, charges remain same. So generalized formula C is equal to Q by V here. So they asked to find out that V value. Q divided by C of S, 24. So what's that value of charge here? 24 here. Milli means 10 to the power of minus 3. So divided by 12 by 7. So this is also millifarad. 10 to the power of minus 3 term will getting cancelled out here. So 7 goes to numerator. 7 into 2. 14 here. So what's that answer here? Answer is 14 volt here. So we'll look at next one. The charge on capacitor is 30 microcoulomb. So on capacitor is there. Charge on that capacitor is 30 microcoulomb. So Q value is how much? Q value is 30 microcoulomb. It is connected to another capacitor of half of its capacitance in parallel. So let me take initial capacitance. C1 value is C here and C2 value is half dimension. So took it as a C by 2 and these two capacitors they said that connected in parallel. So what is that nature of combination here? C of P. First let me find out that effective capacitance in parallel combination. So this is the connecting formula. C of P is equal to C1 plus of C2 here. So C of P, C1 value is C, C2 value is C by 2 here. 2C plus of C here, 3C divided by 2. What is that effective capacitance here? 3C divided by 2. Then charge on the first capacitor is, so which thing they asked to determine here? Charge on the first capacitor. So in order to determine that charge on the first capacitor, so that is nothing but a branch charge. So branch charge is equal to total charge into capacitance of that same branch. First capacitor value is how much? C here divided by total capacitance C1 plus of C2. Q value is how much? 30 micro. So 10 to the power of minus 6 here. 30 into 10 to the power of minus 6 into C divided by 3C by 2. So this is also in terms of 3C by 2 only. So C term will getting cancelled. 10s are 20. So 2 goes to numerator. So 20 into 10 to the power of minus 6 or 20 microcoulomb. What is that charge on that first capacitor here? Charge on the first capacitor is 20 microcoulomb here. Okay. We'll look at next one. two spheres of radii 12 centimeter and 16 centimeter have equal charge. So two spheres are there, so it is having that radius, it has radius 12 centimeter and 16 centimeter here. So they mention on these two body having equal charges, ratio of their energy is. So I am having that energy stored in case of capacitor three different form, q square divided by 2 times of c, half cv square and half of q into v. But in this particular question, so they mentioned that charge is remains, sorry, one second. So charge is remains, means equal charge. So for that equal charge, q square divided by 2 times of c. Energy is inversely proportional to capacitance here. So energy is inversely proportional to capacitance means, so for that sphere, so capacitance of a isolated sphere, so that is c is equal to 4 pi epsilon naught into r. So what's that connecting formula? U is inversely proportional to r for same kind of charge. So u1 by u2 is equal to what? R2 by r1 here. R2 value is how much? 16. R1 value is how much? 12. So what is our answer? So ratio is 4:3 here. So hope you are understanding. Okay, we'll look at next one. A charged sphere is connected to a similar uncharged sphere, then percentage loss of energy is. So look at here. A charged sphere is connected to a similar uncharged sphere, then percentage loss of energy is. So what is the connecting formula for loss of energy? Half of C1 into C2 divided by C1 plus of C2 V1 minus of V2 of whole square. They mention that uncharged capacitor means again that V2 value I will take it as a 0 here. So look at here. So they mention that similar similar capacitance. So C into C. So that is C square. C plus of C. 2 times of C here. So V1 square. So look at here. 1 by 4 C into V1 square. So shall I take this one as delta of U is equal to 1 by 2 into 1 by 2 C into V1 square. So this is nothing but an initial energy stored. So delta of U is equal to U of I divided by 2. So initially is 100% means half of the initial means, so that the answer is 50%. So half of the initial value here. So what is that answer here? Answer. Okay. So we'll look at next one. Three condensers of same capacity are connected in series, has effective capacitance 2 millifarad here. So how many number of capacitors are there? 3 capacitors. If they are connected in a series combination, so they mention that effective capacitance is 2 millifarad. If they are connected in parallel and charged using a battery of 12 volt, then energy stored in the combination is, if it is connected in a series combination, its effective capacitance is 2 millifarad. If it is connected in a parallel to a potential of 12 volt, what about that energy stored? So they given that answer capacitance in series combination, but they didn't mention the value of capacitance in parallel combination. First I will consider that what is the effective capacitance if 3 capacitors are connected in parallel combination. So for that purpose, in series combination, effective capacitance is C by N. C of S is equal to how much here? 2 millifarad. C divided by N value is how much? So 3. So will you get that C value here? So C value is, so C is equal to what? 6 millifarad. So C value is how much? 6 millifarad. So in parallel combination, C of P is equal to what? N into C. N is how much? 3. C is how much? 6 here. C of P is equal to what? 18 millifarad here. So now I want to find out that energy stored in parallel combination. So U is equal to half of Cp in, so U is equal to what? Half of C of P. So C of P means what here? So C of P is equal to what? So C of P value is 18 here. 18 into 10 to the power of minus 3 V square. So 12 into 12 here. So 9 here. 12 into 12 is 144. 144 into 9 here. So 144 into 9, 36, 36 plus 3, 39 here. So 1296 into 10 to the power of minus 3 joules, or 1296 millijoule I will consider. What's that? Okay, we'll look at next one. Work done in increasing the potential difference of the plate of a capacitor from 4 volt to 6 volt is W. So work done to increase the capacitance, increase the capacitance from 4 volt to 6 volt is W here. So initial case U1 is equal to W. Further work done in increasing the potential difference from 6 volt to 8 volt is U2 value I need to determine. So energy stored in the capacitor in the first case and in the second case. What is the generalized formula? C into V square. Here that from 6 volt, so from 4 volt to 6 volt and 6 volt to 8 volt, V1 square or V2 square minus of V1 square in that first case, divided by, in the second case same, that V2 square minus of V1 square in that second case. Half of C will getting cancel out here, U1 by U2, so that is equal to, in that first case V1 value is 4 volt and V2 value is 6 volt. In that second case V1 value is 6 volt, V2 value is 8 volt. So in the first case V2 value is how much? 6 square here, this is 4 square. Second case V2 value is 8 square, here this is 6 square. U1 how much they mention? U1 is equal to W. U2 value is yet to be determined. So 36 minus of 16 divided by 64 minus of 36 here, W divided by U of 2, 36 minus of 16, so that is 20. So 64 minus of 36 here, so 64 minus of 36, so it is 28 here. 4 5s are 4 7s. Okay, U2 is equal to what? 7W by 5 here. What is that answer here? U of 2 is equal to 7W divided by 5 here. So we'll look at next one. A 20 farad capacitor is charged to a 5 volt isolated. It is then connected in parallel with uncharged capacitor of 30 farad here. So C1 value is 20 farad and C2 value is 30 farad, and C1 is connected to a potential of 5 volt and V2 value is 0. Why? Because uncharged dimension. So V2 value is 0 for uncharged capacitor. The decrease in the energy of the system is, so decrease means energy loss. Same formula, half of C1 into C2 divided by C1 plus of C2, V1 minus of V2 of whole square. Simplify this value. So C1 into C2, 20 into 30, 20 plus of 30. So V2 value is 0, so that is V1 value is 5. So half of 20 into 30 divided by 50 into 25 here, 25 ones are 25 twos are here. So delta of U is equal to right. So 600 divided by 4 here. So delta of U is equal to what? 300. So that is 150 here. So what is that answer here? Decrease in the energy is 150 joules here. So decrease in energy is nothing but a energy loss. So this is the amount of energy loss I need to consider here. So we'll look at next one. Okay, look at next one. If the body is if the charge on a body is increased by an amount of 2 coulomb here. So one body is there, on that body the charge is going to be increased by 2 coulomb, energy stored is increased by 21%, then original charge on the body is, so let me take that initial charge or original charge is q1 is equal to q here, q2 value is q plus of 2 times of coulomb here, so q plus of 2 times of q here, so that is increased by 2 coulomb dimension, energy stored increased by, so 21% here, initial energy is 100% you can take, final energy is, so 21% increase means 121 here, so energy stored initially is 100, so finally is 121, then original charge on the body is, what is the connecting formula here, energy here, so energy is equal to q square divided by 2 times of c here, energy is directly proportional to square of the charge here, so u1 by u2 is equal to square root of q1 by q2 here. So look at here, u1 by u2 is equal to, initial charge is how much here, so initial charge is q here, okay, and so final charge is q plus of 2 here, and u1 is how much here, u1 is 100 here, and u2 is 121, so under root q divided by q plus of 2, so taking that square means, so if it goes 100 square is 10, 120 means 121 means that is 11 here, so shall I take that 10 by 11 is equal to q plus of 2 here. So let me find out that q value here, so 10 into q plus of 2, it is equal to 11q here, 10q plus of 20, it is equal to 11q here, so 11q minus of 10q, 11q minus of 10q is equal to what, 20, 11q minus of 10q is nothing but q, so what's that charge value here, charge value is 20 coulomb here, so what's that answer here, q is equal to 20 coulomb here. So we look at next one, force acting upon a charged plate kept between the plates of a charged capacitor is F here. So look at here, force acting upon a charged particle kept between the plates, so two plates are there between the plate, so that force exists is F here. If one of the plate is removed, then force acting on the same particle will be, so look at here, I will read out the question once again, force acting upon a charged particle kept between the plate of a charged capacitor is F. So initial force is F here, if one of the plate is removed, then force acting on the same particle will be, so look at here, initial force is F here. Okay, so if one of the plate is removed means, so for example it is positive and negative plate, between these two plate electric field is exist, so that electric field is sigma by epsilon naught, because of the positive plate electric field ends are outward and this one is inward, sigma by 2 epsilon naught plus sigma by 2 epsilon naught, electric field is sigma by epsilon naught here, so force F is equal to E into Q here, sigma by epsilon naught into Q here, so what's that force value here, initial force value is sigma divided by epsilon naught into q. Now they mention if one of the plate is removed, so it is act like a infinite plane sheet here, so in that situation what is the electric field value here, sigma divided by 2 pi, so 2 epsilon naught, why, because of the single plate, so E is equal to sigma divided by 2 epsilon naught, in the first chapter you derived that expression here. Then final force is what, so final force F of F, so final force is final electric field into charge, so final electric field is what, sigma divided by 2 epsilon naught into Q. Look at here, sigma by epsilon naught into Q is nothing but what, initial force, sigma by epsilon naught into Q, so that is initial force, final force is equal to initial force divided by 2, so force is decreases half of the